Okay, guys, welcome to the second lecture that we're having online. We're going to be continuing with chapter 18 about weak acids and bases. The beginning is just a review. So we reviewed basically last time, just to kind of go back for a moment. We reviewed how we might write the acid dissociation equations for a weak acid or a strong acid. We have the acid here. We have the acid and water. And here's the proton, the acid. Again, you can recognize an acid because it'll have an H written in the front. That is going to be the proton, or the H plus ion that will come off. We can write the acids with or without water. So underneath here, just to review, I'm going to show you how you could write this without water for acids. But usually in your textbook and on the McGraw-Hill Connect questions, they do include the water here. So we have an acid in water, and the acid is, what makes an acid is that it gives up H plus 1 ions. So this H is going to come off, and when it does, it leaves these 2 electrons behind. And so you can see that what we have left of what we're going to call the conjugate base, or what we have left after the H plus is gone, it has these extra 2 electrons now as a lone pair. The result is that it has a negative charge. The easy way to remember this is when you lose an H plus, the charge goes down by 1 unit, from 0 here down to -1. Now the H plus ion went over to the water. So again, this H takes no electrons with it. These 2 electrons are going to form a coordinate covalent bond with the H plus, and there it happens. And now the oxygen essentially lost an electron because it has to now share it with hydrogen. So the result is that we get this whole polyatomic ion that is +1. This is called hydronium. And it's in your list of polyatomic ions. We just haven't talked about it much until now. And again, so just like if you lose an H plus, your charge goes down by 1 here from 0 to -1 for the conjugate base, A minus. If you gain an H plus, like here, the H plus was gained, your charge goes up by 1 unit from 0 up to +1. Now, another way to write this, if we were just writing this in general, would be to call this HA again. HA. Oh, whoa, something weird's happening with my pen there. And we could just say, okay, HA is going to then separate, and I'll use these 2 arrows, into H plus. This is a weird thing happening with this pen. Plus A minus. Okay, and so H plus and H3O plus, these 2, these are kind of interchangeable, meaning they can, you can write H plus, or you can write H3O plus aqueous, and you mean the same thing. Because when you have an H plus in water, that H plus is actually going to be attached to the water generally. So you can write the equation this way, and I'm going to erase my writings here. So you can write it in this way, or you can write it as HA makes H plus aqueous and A minus. Either way is okay, but generally your book is going to do it this way. So that's why that's the way I show. And remember the definition of conjugate acid base. Here HA is the acid because it's providing the H plus. What you have left after the H plus is gone is called the conjugate base. For the water, in this case, it's acting like the base. When it picks up an H plus, now you have hydronium. That's what water makes when it gains an H plus. So that is called the conjugate acid. And when we have 2 of these separated by 1 H plus, so the difference between water and H3O plus is 1 H plus, we say that they are conjugate acid-base pairs. The HA and A minus, they differ by 1 H plus, so they are also conjugate acid-base pairs, we would say. A minus is the conjugate base of HA is the conjugate acid of A minus. Questions about this acid dissociation or about conjugate acid-base pairs for now?
No.
Okay. Now for the weak base dissociation, and you guys can always interject with questions, feel free. The weak base dissociation, if it's a weak base, it's written with water. And that's because for the weak base is going to be accepting a proton. If we have strong bases, they all have hydroxides. The base is hydroxide. But with a weak base like this, NH3, it's going to be accepting a proton from the water. So we have to write the water because that's where the proton is going to come from. So here you can see in the last case, water was acting like a base. In this case, water is acting like an acid. It's going to give its H+. The H+ is going to attach here where the nitrogen is. And what we'll have left of the NH3 is now NH4+. Notice that an H is added and the charge goes up by 1 unit from 0 here. Going back to my laser pointer. From 0 right here to +1. So when you gain an H+, your charge goes up by 1 unit. Don't forget that. And the water lost the H+, so now it only has one H and one O. It's hydroxide. This is the Lewis structure. And its charge has gone down by 1 unit because it has lost an H+. So it goes down from 0 down to -1. Okay. Now you may wonder, well, why is it that when we added the acid, so why is it when we added the acid, the water acted like a base? But when we added a base, the water acts like an acid. Well, it all depends on which of these would hold on to the H+ more strongly. Essentially, which is the stronger acid, meaning wanting to give up the H+, and which is the stronger base, wanting to hold the H+. So in the case of this base dissociation, the water was the stronger acid and the NH3 was the stronger base. In the case of this, the HA was the stronger acid and the water was the stronger base. As you can see, water can act like both an acid and a base. The term for that is amphoteric. You might see that in your book. So if we're going to try to decide whether this reaction will go or not, or how it will go, the stronger acid will behave like the acid and the stronger base will behave like the base, and ultimately they will make a weaker acid and a weaker base. That's what drives this reaction. The stronger acid is willing to give up the proton more easily, and the stronger base is willing to take it more easily. It wants to stick to that proton, the stronger base. So how are we going to quantify what's a strong base, weak base, and how will we recognize them? Or strong acid, weak acid? Well, we're going to use K values. So we had, in the last chapter, it was all about Kc and Kp. And we're going to basically get a Kc for each of these reactions. So we're going to get a Kc for the acid dissociation type reaction. We're going to end up calling those Kas, give them a special name. They're just normal Kcs like you've been doing in the last chapter. For base dissociation, we're going to have a Kc for this type of reaction. We're going to call those Kb for the base. So for example, in the Kb for the Kb for this reaction, or the Kc for this reaction rather, would be called the Kb of NH3 or ammonia, because it is the K for the reaction of the ammonia acting like a base. So that's what we're gonna work towards in this chapter as we continue. So when we say weak acid or strong acid, what does that mean exactly? Well, for a strong acid, what it means is that if you put this strong acid in water, it will completely separate from its proton. We call this 100% dissociation. So for a strong acid, the reason why we call it a strong acid is because once you have put it in water and waited a small amount of time, the proton connected to the conjugate base of that strong acid basically is not present anymore. It's all separated protons, and they're separated from the conjugate base. So remember, another way to write this would be here we could say HA is going to 100%, so I'll write a one-way arrow, 100% separate into H plus and A minus. And remember, I don't know why that's happening right now, but remember that H plus and H3O plus are essentially interchangeable. We could write either one. Your book tends to write H3O plus more. This is kind of a simpler way of writing the same thing for acids, just for acids. So we call this a strong acid because all of the H pluses have popped off of the A minuses and now attach themselves to water instead. And we can see that in this picture here. For a weak acid, you're still going to have some of the H plus attached to the A minus being, again, just any general anion that's going along with the H plus in the acid. But some of it will be separated. So some of the H pluses will have popped off, like here the H plus popped off the A minus and attached to water. But for these molecules, it didn't. And so you can see here that it was only partially dissociated. Still, some of the H plus is attached to the HA. If you have a very, very weak acid, it will produce essentially no H plus or H3O plus. It will be basically no dissociation. So all of the H pluses will stay attached to the A minuses, as you see here. So that's what makes, that's the difference between a strong acid and a weak acid, okay? So how can we identify a strong acid or a weak acid? Well, there are 6 strong acids that you're going to have to memorize. 4 of them are up here. HClO4, perchloric acid, HCl, H2SO4, and HNO3. There are 2 more. I'll write them up here right now, assuming my pen will work. It's going to be HBr and HI. Those are the 6 strong acids. And so these, you'll notice that these are hydrohalic acids. So HCl, HBr, and HI are all strong acids. These are the 6 strong acids. For these, you can assume 100% dissociation in aqueous solution. For the rest, they'll have various strengths. Some are stronger than others, and we're going to use the Ka to describe how strong one is relative to another. But thinking about what it means for an acid to be strong, so let's go back and say, okay, when an acid is strong, what does that mean about when we put it in water?
It wants to give an H plus ion.
It wants to give an H plus, and it's all of them are going to give the H plus, right? All the molecules in there, or all the acid molecules, I suppose you'd call them. They're kind of like ionic compounds too, acids, but they will completely separate from their H plus 1 ion, which means that once you have the conjugate base, so here perchlorate is the conjugate base of perchloric acid. Oh my God, I have to remember how to name these things. Yes, you can't forget that from the beginning. But yeah, so this is the conjugate base of perchloric acid. It's what you have after the H plus has gone. Notice when you remove an H plus, you lose the H isn't there anymore, and the charge goes down by 1 unit from 0 down to -1. So this is the conjugate base of the strong acid perchloric acid. This base is going to be a terrible base. So remember what it means for something to be a base. What it means is that it wants to grab protons. The stronger the base, the more it's going to stick to protons. Well, this conjugate base of a strong acid will be a terrible base because the strong acid wants to completely separate from its protons. It doesn't want to grab them back. So the stronger the acid you have, the weaker is the conjugate base. And the weaker acid you have, so for example, water is not a very strong acid. its conjugate base, hydroxide, is very, very strong. We consider hydroxide to be basically the definition of a strong base, hydroxide itself in water. And so water itself is quite a weak acid. And you can see that HSO4 minus is a pretty strong acid. This is because sulfuric acid itself is a strong acid. This one has a second proton to lose. So we'll talk about what happens when acids have 2 protons that they can lose. Notice sulfuric acid is like that. So is phosphoric acid. Okay, and so these are getting weaker, weaker, weaker acids. So the weaker the acid, the stronger the conjugate base. So perchloride ion, terrible, terrible base. Fluoride ion, okay base. Hydroxide, awesome base. And then any of these compounds here that are considered bases, their conjugate bases are very, very strong bases. They're stronger than hydroxide even. If you put these in water, they're going to turn to hydroxide in ways that we'll talk about later. So basically, the stronger the acid, the weaker the conjugate base. Also, the stronger the base, the weaker the conjugate acid. So they go opposite to one another.
For the conjugate bases for HBr and HI, it would just be Br and I, but with a negative?
Yeah, so the conjugate base for bromide, yeah. So if you ever want to figure out the conjugate base, which you'll have to do, take off the H and put the charge down by 1. So bromide, your HI, take off the H and put the charge down by 1, from 0 down to -1. Ah, that's so weird that it started doing that this morning. I minus, okay. Other questions here about acids and their conjugate base and their relative strengths?
No.
No? Just let me know, guys. I'll try to, give a little pause so you can ask a question, but I know sometimes you got to type it or whatever. So if you still have a question later on, don't, feel free to interrupt me. That's just the, being online. There's going to be a delay sometimes. So how can we, just by looking at the formula of a acid, get an idea of how strong or weak the acid is? Well, when it comes to the to acids that are just a proton and another atom, like the hydrohalic acids, the strength of the acid all depends on the strength of the bond between the hydrogen and the other atom. So if that bond is very weak, then the H plus can pop off very easily. That makes for a strong acid. If the bond is strong, this means that the H cannot pop off as easily. So that makes for a weaker acid. So you can see here in terms of these hydrohalic acids, the hydroiodic acid is the strongest of the acids. This is because it has the longest bond. Bonds tend to get weaker as they get longer. You can think of like if you're trying to karate chop, a plank of wood or something. If the plank is short, it's harder to karate chop it. But if the plank is long, the longer it is, the easier it is to chop it. So bonds are kind of like that too. The HI bond is longer because iodine is a much bigger atom than fluorine is. So it's easier to karate chop this bond. And so that means the H plus pops off easier. And the HI is the strongest of these acids. And as the bond gets shorter and shorter because the atoms are smaller and smaller, the strength of the acid gets weaker. So HF, out of these 4, HF is the weakest. So that's why HCl, HBr, and HI are all strong acids. So you don't really have to memorize that as long as you understand this concept that HF is the weak acid. It's considered weak because its bond is the shortest. Did a cat just walk by? Okay, the cats are playing with the green screen. Okay, so yeah, these bonds are easier to break because they're shorter, and this bond is, they're easier to break because they're longer. Easier to karate chop the long bond. this has the shortest bond. It's hardest to break. So that means that the HF is weaker than the rest of the hydrohalic acids. You love cats? Me too. I have 3 cats. Guys, I need that green screen. Okay, anyway, you're going to see some artifacts on the corner there. That's them messing around with my flat green screen. It's not flat anymore. Okay, anyway. All right, well, I'll wait for this one. I'll go to the next. So what about these guys here? So this this had all of the halogens. They're all vertically arranged. So when these acids have atoms that are vertically arranged relative to each other like this, HF, HCl, HBr, HI, the longer bond is weaker. So the biggest atom, in this case iodine, closest to the bottom, will make the strongest acid. If we're going horizontally like this, so on the periodic table, the carbon is to the left of nitrogen, which is to the left of oxygen, which is to the left of fluorine. So as you're going left to right, it all has to do with the bond polarity. So the more polar the bond is, essentially the easier it is going to be for these to separate into ions, because a very, very polar bond ends up getting weaker and weaker because, for example, with fluorine really loves electrons, right? That's one of the most important things you should remember. Fluorine, oxygen, they freaking love electrons more than anyone else, right? So the fluorine is pulling the electrons so hard its way that it weakens this bond here. And so the result is that the H plus can pop off more easily. And so then you'll get, a stronger acid. So the HF is the strongest of all of these acids. It's the only one that could really be considered an acid. Water can act like an acid, but its bonds are much stronger than those between H and F. And then these guys here, NH3 is actually is not even an acid at all. It's a base. It can end up accepting a proton right here. That's where a proton will usually attach if it's acting like a base. And CH4 is neither acidic nor basic, really. It can't really attach an extra proton, and its bonds are too strong to give them away. Question.
What does the double less than bracket mean?
Oh, this is terms of the acid strength. So what this means, right here, this means much less acidic. So this is less than. So the water is less acidic than the HF. The ammonia is less acidic than the H2O. Okay. In fact, it's not even acidic, it's basic.
Okay.
Yeah, good question. Okay. So this is how you estimate acid strength for atoms attached to hydrogen going across. The last slide was going up and down on the periodic table. Other questions related to that idea? Okay, so we also have a number of oxoacids, meaning they are acids that have polyatomic ions that have oxygens in them. So when it comes to oxoacids, there's 2 things that will affect the acid strength. If you guys are going into organic chemistry, all of this is really, really, really helpful information, by the way. Anyway, so if they all have the same number of oxygens on them, so these all have 1 oxygen, what will affect the acid strength is the electronegativity of the other atom that isn't oxygen. So the more, so in terms of acid strength, the hypochlorous acid here is the strongest of the 3. And this is because it has the most electronegative chlorine atom. The reason why this is because remember what it means for an atom to be electronegative is that it's pulling electrons its way. And so the chlorine here is pulling electrons towards itself. And that means that is weakening this bond right here. Oh my God, that is so annoying. But anyway, it's weakening this bond between the hydrogen and oxygen because the chlorine is pulling quite hard on the electrons in this bond here. This is called the inductive effect. And you'll talk a lot about that if you take organic chemistry. So the result is that the oxo acid with the chlorine in it, the hypochlorous acid, is a stronger acid than the hypobromous acid, which is a stronger acid than the hypoiodous acid. And this is because the stronger pull of the chlorine is weakening this bond here. And so it's easier for the hydrogen to come off. Now, of course, oxygen itself is very, very electronegative. Next to fluorine, it's one of the most electronegative atoms. So in terms of acids that have more and more oxygens in the anion, so this only has one oxygen in the anion. If we have acids that have more oxygens in the anion, the more oxygens there are, the more acidic the acid will be. So when we were talking about acids, whether they're strong or weak, we said perchloric acid is one of our 6 strong acids. And that's because due to the fact that it has so many oxygens, the inductive effect is very strong, weakening this bond between oxygen and hydrogen. And so that results in an easier hydrogen to pop off, a stronger acid. As we have less and less oxygen, this inductive effect is weaker. And so the bond here between oxygen and hydrogen is stronger, stronger, stronger. And so these acids become weaker, 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 because it's harder to get the H plus off. And that's it for the strength of the oxo acids. Did anyone want to ask a question about how to determine the relative strength of oxo acids?
So the more oxygen there is the stronger the acid?
Yes, the stronger the acid, so more strength. And this is because, again, this is a great way to make it so you don't have to memorize what the strong acids are per se. I have them memorized because I've used them so much, but I also know why they're so strong. Perchloric acid is so strong because it has the chlorine atom, which makes it a strong oxo acid. And also, it has 4 oxygens on it. So that makes this inductive effect really strong, weakening this bond, allowing the H plus to come off quite easily. Okay. I know, for example, that HI is stronger acid than HF because it has a longer bond between the iodine and the hydrogen, because iodine's so big as an atom, and that allows the H to pop off more easily. So I don't really have to memorize per se what the strong acids are. I know why these are strong and HF is weaker. And I know why, in general, the hydrohalic acids are strong, right? It's because of the bond polarity. The bonds are much more polar for like HF, for example. Other questions? So I tend to give you, a multiple choice question or two about which acid is stronger, which acid's the strongest, that kind of thing, when we get to that exam. So what about pH? So you guys probably learned something about pH when you were in your Chem 150 class or Chem 101 class, in one of your previous chemistry classes. We're going to be using pH again. And the way pH arises is due to the fact that water, or the reason why pH is good for describing water, and the way we're going to use to calculate water, is understanding that water is amphoteric. So even when it's only water, just pure water, it's possible for one water molecule to behave like an acid and give a proton to another water molecule which is behaving as a base. And so here we have written what's known as the KW equation. The K of this reaction is called KW. So the H plus here is going to come off the acid water molecule. It's going to attach here over to the base water molecule. And so we have hydronium ion being made here. And we can see that since the base gained an H plus, it has one extra H, and its charge goes up from 0 up to +1 because it gained an H plus. The water that behaved like an acid, it lost the H plus, And so it now has one less hydrogen, and its charge has gone down by 1 unit from 0 down to -1. This is hydronium, and this is hydroxide. So in order for something to be considered an acid or a base, it's always in the context of water. And what acids do in bases or in water is they make hydronium ions. And what bases do in water is they make hydroxide ions. If there is an acid that is stronger than water in water, it will end up giving its proton to water and making hydronium. So hydronium is basically is the strongest acid there is in water. If you want a stronger acid, you'd have to be considering solutions that are not aqueous, not in water. There is some research about those kinds that happen at UCR. Actually, there was a guy named Reed, really famous for that. He was Dr. Avalar's research advisor when she got her PhD. And then in terms of bases, any base that's stronger than water would pull a proton away from the water. So it will make hydroxide ion. So hydroxide ion is the strongest base that you will realistically have in water, because if you had any stronger base, it would take the proton from the water and make hydroxide. This is referred to as the leveling effect of pH. So acid basically in water is hydronium, and base in water is hydroxide. And because there's this equilibrium here, there will always in water be a relationship between the concentration of hydroxide and the concentration of hydronium. It will be dictated by this equilibrium. So writing down the equation for this not in Lewis structures, but in regular terms, we have two water molecules here, two water molecules. And then as a product, we have one hydronium ion, H3O+, and we have one hydroxide ion. So in pure water, every time one water molecule reacts with another, we'll get hydronium ion, we'll get hydroxide ion. So in pure water, these would have to be the same, because in pure water, every time you make one hydronium like this, you'll make one hydroxide. In terms of writing the K for this reaction, let's say you were to write the Kc, right? You're going to say, okay, products, hydronium ion and hydroxide ion on top. Then on the bottom, we put the reactants, but we're not going to put water. Why wouldn't we put water in our Kc equation?
It's liquid.
It's liquid. It's not aqueous, right? We only include aqueous or gases in the Kc because those are the ones that can move around and affect the relative rates of the forward and the reverse reaction. So our Kc for this reaction actually gets a special name. We call it Kw. Kw is the Kc for this specific reaction. It is products, hydronium hydroxide on top, over reactants, nothing, because we don't include water. And if we have pure water at 25 degrees Celsius, we can measure the concentration of hydronium and hydroxide. We would find them to both be 1 × 10⁻⁷ in pure water at 25 degrees Celsius. This is because, well, they have to be the same, because every time two water molecules react in this way, they're going to make one hydronium and one hydroxide. So of course, in pure water, they're going to be the same. And these are those concentrations. If we want to calculate the value of the Kw, we would multiply the equilibrium concentration of hydronium times the equilibrium concentration of hydroxide. And so we've plugged that in here, the equilibrium concentration of hydronium here, the equilibrium concentration of hydroxide here, and we get a Kw value of 1.0 × 10⁻⁴ at 25 degrees Celsius. You're going to be using this value all the time. So you'll probably end up memorizing it quite easily. It's not too hard of a number to memorize anyway. Of course, you can always look it up. You guys are online, you got Google. You can look up what is Kw if you want. They'll tell you that's it at 25 degrees Celsius. So this is going to be really important to us, because often we're going to know hydronium concentration in a solution, but we won't know hydroxide, or we'll know hydroxide and we won't know hydronium. But because of this leveling effect of water, there'll always be a relationship between them. And so we can figure out one or the other if we have one. So in general, Kw, which is the hydronium times the hydroxide concentration, is this value at 25 degrees Celsius. So let's say we want to find the concentration of hydronium. Well, we could divide by the hydroxide concentration. Okay, that will cancel hydroxide concentration. We'd have to do it on this side too. And so we get that the hydronium concentration equals Kw over hydroxide. Okay. Oh, geez. Okay. So hydronium concentration, which we solve for right here, equals Kw over hydroxide. So if we ever have the hydroxide concentration and we want the hydronium concentration, we just take 1 times 10 to the minus 14 and divide by the hydroxide concentration. We get hydronium. Okay. Now, similarly, if we wanted eraser, I can't erase, why? Okay, similarly, if we wanted hydroxide concentration, we would divide both sides by hydronium concentration. And so hydroxide concentration will be Kw divided by hydronium concentration. So if we have one of these, if we have hydroxide, we can get hydronium by using this. If we have hydronium, we can get hydroxide by using this. And so the Kw equation is going to be really, really valuable for us. Questions on that idea? So now back to this acid-base leveling effect. So what we're saying is that if this number for hydronium is higher, then this hydroxide number has to be lower if they're still going to multiply to 1 times 10 to the minus 14. If the hydroxide increases, then the hydronium must be smaller because of this acid-base leveling effect in water. Their concentrations in water must always multiply to the Kw. So if we've got pure water or a neutral solution, that means that hydroxide and hydronium will be the same. They'll be 1 times 10 to the minus 7 power in molar concentrations. However, if we have a higher hydroxide concentration, the hydronium concentration must be lower so that they'll still multiply to 1 times 10 to the minus 14. So if we add acid into solution, this will increase the hydronium concentration and decrease the hydroxide concentration. On the other hand, if we add base into solution and increase the hydroxide concentration, that means there must be a decrease in hydronium concentration because always their values must multiply to 1 times 10 to the minus 14. Questions there? The number of moles? Usually, so this is a very good question in terms of talking about things in terms of moles or molarities. So remember, when it comes to Ks, always involved in the K is the concentrations, right? So these will have to be molarities. But it's also true if there's more moles of acid in there. Well, if everything's in the same volume, this is a trick we used in chapter 17. We can replace moles with molarities. And that's usually what we're going to do. If we're given moles, we'll usually try to get them into molarities as soon as possible because you need to be plugging in molarities for the K values to work right. And so we won't be using moles as much. In fact, just like we did in chapter 17, we're going to continue to do our stoichiometry a lot of the time in molarities instead of moles, as long as the volume doesn't change. When we get to chapter 19, we're going to have situations where the volume will change. And so we'll have to recalculate the molarities for the new volume. But I tend to go straight to molarities. And this is something your book doesn't always do. I feel like the way your book describes some of the calculations is not as easy as the way I will describe them to you. And so, yeah, for that reason, we could use moles, but the way I'm going to teach you is we're always going to be working in molarities. It's just generally better. So did that help? Or did I miss the point? So for Connect, generally it's going to ask you for the final answer. And that final answer will usually be a molarities or a pH or something. Sometimes they ask for moles too. But you do need to know how to go between moles and molarities. So what conversion factor do you need to go between moles and molarities? Moles and volume. I messed up that question, but molarities, yeah. So if you want molarities, you just take the moles and divide by the volume, right? And if you have the molarity in the volume, you can find out how many moles. And so that's something we've done a lot of already in this class. But you can be asked about how many moles and what is the molarity. However, when we're doing our work, we're going to want to work in molarities generally. We can always figure out the number of moles at the end, or if we're given moles at the beginning, turn them to molarities to do our work. But the way I'm going to show you to do the work is to pretty much always be working in molarities to do your stoichiometry and stuff. It's just easier that way. But you should be able to convert between moles and volume, or take the moles and divide by the volume to get the molarity, since we've done a lot of that already, right?
I wonder if she was asking, because when we did the ice tables and we got the K's, how we used the moles as exponents to get our equation.
Oh,
I wonder if that's what she was asking.
Now I understand the question, right? So in the case of KW, the exponents are 1 and 1, because here the coefficients are 1 and 1. There are situations, not as much in acid-base chemistry, but there are situations where we'll have a coefficient here and we'll have to square or something. But yeah, definitely when you're writing K's, it's the same old K. Nothing's changed. The reason why the exponents here are 1 is because the coefficients are 1. If the coefficients were something different, the exponents would be something different. Yeah, but here the exponents are 1. So for this calculation, it's always going to be an exponent of 1 for hydroxide and hydronium. Thank you for clarifying that, yeah. But basically, we're just expanding upon our idea of KCs. We're going to be using a lot of KCs. We're just applying these now to acids and bases. But the way we do K is no different. We just give them a different name, like Ka, because it's the KC for an acid, and so forth. So you might have noticed talking about the concentration of hydronium and hydroxide is not very convenient. It's not convenient to say the concentration of hydronium right now is 1.0 times 10 to the minus 9 molar. That's a big, long sentence, okay? So instead of talking about concentrations of hydroniums, a lot of times we convert these into a scale known as the pH scale. The pH scale makes it very easy to talk about what the concentration of hydronium is. If the concentration of hydronium is 1 times 10 to the minus 7, that's neutral. Then we say the pH is 7. That's neutral. If the concentration of hydronium is larger, so this is getting larger and larger numbers because the negative exponents are smaller. We have larger concentration of hydronium. We say the solution is acidic. So these solutions would then have pHs of lower than 7. If the concentration of hydronium is smaller than a neutral solution, then we have a pH that is basic. So what is the definition of the pH? The pH is the negative log of the hydronium concentration. So remember that log cancels 10 to the power of something, right? So let's say, for example, we wanted to know what would be the pH if the hydronium concentration, is 10 to the minus 6. Okay, well, the pH then would be the negative log of 1 times 10 to the minus 6, or just 10 to the minus 6. Okay. And remember what log means here. Log means that we cancel the 10, right? So log is going to cancel the 10. And so then what we've got is so we got equals minus a negative 6, because the log canceled the 10 to the power. And so then the negatives cancel one another. Negative cancels negative. And we get that the pH equals 6. So that is showing you that if the concentration of hydronium is 10 to the minus 6, that means the pH is 6. So when you have 1 times 10 to the power of you know, a whole number here, 1 times 10 to the power of something, it's pretty easy to get the pH as long as you know the way logs work. Log cancels 10 to the power, a base 10 log. A natural log cancels e to the power. Right? That's some stuff we've done when we were in chapter 16. Okay, so the pH is a negative log of hydronium. If you have a different number here, you would have to use your calculator. And so that's what we're going to be doing most of the time, is we're going to punch negative and then log and then put numbers in our calculator. There's also a value known as, and doing some algebra here. So you guys should be remembering your algebra. Remember, log cancels 10 to the power. Also 10 to the power cancels log. So if we multiply each side by -1, so multiply times -1, this becomes negative, and this negative is canceled. So we get pH, or negative pH rather, equals log of the hydronium concentration. And then we want to get what is the hydronium concentration. That's what we're solving for here. So how do we get rid of this log?
It's base 10.
10 to the power, right? Yeah. So we do 10 to the power of log, and then 10 to the power of negative pH. We do 10 to the power of both sides. When we do that, the 10 to the power is the opposite of log. It cancels it. And so we get that the hydronium concentration is 10 to the negative pH. And so that is what's right underneath on my slide. So hydronium is 10 to the negative pH. Now there's also a value called pOH, which, like pH, is just the negative log, but it's the negative log of the hydroxide concentration instead of the hydronium concentration. We can also do the same type of algebra, multiply both sides by -1, take 10 to the power of both sides, and we have concentration of hydroxide is 10 to the minus pOH. These definitions of pH and pOH, you should have these memorized, okay? This is really important. You should always have these available in your mind. This is what pH means. This is what pOH means. So as long as you memorize this one right here, pH, I think memorizing everything else is pretty easy. So you can do algebra to get to here, and pOH is just the same as pH. It's negative log of hydroxide instead of hydronium. And as you can see here, acidic solutions are those with pH that are less than 7. Neutral means the pH is 7, or the concentration of hydronium is 10 to the minus 7. A basic solution will have pHs greater than 7. And here are some examples of things that are acidic. Experiment 8 is going to be all about converting from pH, hydronium, hydroxide, for all these different types of household items, kind of a lot of these ones here. You'll watch a video about that and convert. So when we, basically at the end of this lecture, I'll talk about experiment 8, and you are free to get started on experiment 8 whenever you want. It won't be due for a little while. but I've assigned it for you to do after you do your exam next week. So any questions on any of the algebra I did there? Okay. Now a note, I just want to remind you guys, at the beginning of the class, I handed you a handout about how to deal with sig fig rules for pH, or for logs. We're going to be doing a lot of logs again in this chapter, so remember how it works. If you take the log of a number, you should write the answer so that it has the number of decimal places that are equal to the number of significant figures in the number you're taking the log of. And if you are going to take the anti-log of a number, you're going to write the anti-log with the number of significant figures that are equal to the number of decimal places in the number. So remember to keep that worksheet handy that I gave you. It's posted also in way back in the beginning when we first started logarithm rules. So sig fig rules for logarithms will apply here. Now, in the example I showed you previously, what we had done was we had taken the negative log of a number that was 1 times 10 to the power. What about this? So we could ask, what is the pH of a solution that has hydronium concentration 0.025 molar? For this, you'll need to use your calculator, or 0.0025 molar. For this, you'll need to use your calculator. So I'll be using this Windows calculator here to show you guys. It has an EE button. So I'm going to write negative log. Oh, mine works like a single line input. So I'll have to type things in like a single line input calculator. So I'd put the number in 0.0025, and I want to take the log of that. So I'm going to press the log button, log. Okay, and then I need to change the sign. That's this button here, plus minus, because I'm multiplying by -1. Or I could just say times -1 equals, or just change a sign there. So that's multiplying by -1. And so when I write my number now, I have to look at how many sig figs. This has 2 sig figs, the 2 and the 5. Front zeros are never significant. So I round my number so that it has 2 after the decimal. 2.60 is the pH. So that's how we'll calculate pH if we have the hydronium concentration. But a big part of what we're going to do, for weak acids is going to be to try to find the hydronium concentration. Questions on how, you guys, hopefully you have your calculator with you and are punching along with me. So just like in class, when I do, you want to have your calculator here during lecture so you can punch along. And if you don't get the same answer as me, let me know so I can help you to punch it in. Okay, so here's another one. This one will involve an extra step. It says calculate the pH of an ammonia solution that has hydroxide concentration 0.0019 molar. There's a couple of ways you can approach a problem like this. You can get the pOH first, or you can get the hydronium concentration first. And I'm going to show you both ways. So if you want to get the hydronium concentration, so remember, well, let's remember what we have here, Kw, right? Kw. So what we need here is we need hydronium concentration, because pH is going to be the negative log of the hydronium concentration. Man, this is coming out bad. I don't know what's going on there, but I was doing this yesterday just fine. But anyway, so it's going to be the negative log of the hydronium concentration, but we don't have the hydronium concentration. We have the hydroxide concentration. But we have a way to get the hydronium concentration. It's Kw. Kw is hydronium concentration times hydroxide concentration. And that is always 1 times 10 to the minus 14 as long as we're at room temperature. Of course, equilibrium constants do change with temperature. So if we divide both sides and solve this for the hydronium concentration, we get hydronium concentration is 1 times 10 to the minus 14 divided by hydroxide concentration. So we can now put these in. So we put 1 times 10 to the minus 14 in, that's Kw. We put the hydroxide concentration, 0.0019. And now we have to calculate it. So I've got the answer there, but let's calculate it. Remember, when you're using your calculator, am I going to type times 10 to the power of negative 14? Do I type that?
No.
No, no, never, never, not times, right? We're going to use our EE or our EXP or our button specifically designed to go times 10, then our negative 14. So on my calculator, it looks like this. 1e negative 14. This means 1 times 10 to the minus 14. I'm going to divide by 0.0019. And I get this number. This computer calculator is kind of nice because it can write as many zeros as it wants to. However, I want to show this in scientific notation. Oops, something went wrong, I feel like. 1.0 EE minus 14 divide by 0.0019. There we go. And so our calculator shows us 5.263 times 10 to the minus 12. Since this had 2 sig figs here, our Kw is also written with 2 sig figs. We'll write our result with 2 sig figs. Since this is a 6, we round the 2 up to a 3. And so we say 5.3 times 10 to the minus 12. Questions there? So now we have the hydronium concentration. So the pH is a negative log of the hydronium concentration. That's this right here. So we're going to take this, put it in for the hydronium concentration. We take the negative log. So I'm going to put 5.3 EE negative 12. I'm going to take the log of that, log, and then I'll change the sign by multiplying by negative 1. And so we get 11.28. Remember how your sig figs work for logs. If you're taking the log of a number with 2 sig figs, you write the results so that it has 2 after the decimal. And so our result is 11.28. Questions there?
No.
No.
Good. Doing okay? All right. So let's continue. We can also go the other way. So if we have pH and we want to calculate the hydronium concentration, remember that the hydronium concentration will be the antilog of negative pH. Just going back, I derived that earlier when we multiplied both sides by negative 1, and then we took the antilog. So hydronium concentration is 10 to the minus pH. So we're going to use that fact here. The pH of the lake is 4.5. It's acidic because of acid rain. And so the hydronium concentration will be the antilog of negative 4.5. Notice we are taking the antilog of a number with 1 after the decimal point. So our result needs to be rounded to 1 sig fig. Now putting this in your calculator, the antilog button is usually right next to your log button. So I have to do this like a single line calculator. So I would put negative 4.5 and then I'd take the antilog of that right above the log button here. And my calculator tells me 3.1622 times 10 to the minus 5. But I'm going to round this to 1 sig fig because I'm taking the antilog of a number that has 1 after the decimal. Okay, So I would round this to 3 since this is a 1, and I state my answer is 3.3 times 10 to the minus 5 molar. Very important, note that pH does not have a unit behind it, but concentration does. I do look for those units. I want you to write the unit on your labs, and if you know, if you're selecting a choice on the or putting an answer in the homework problems, you often need to put the unit. So make sure you put the unit. Okay. Now, in the past, you may have used acid-base indicators, and acid-base indicators are really useful if we're mixing acids and bases, or we have an acid and base, we want to know its range of pH. Often when we're mixing acids and bases, we want to know when a pH has changed from one pH to another pH along the pH scale. So the way acid-base indicators work is there's some organic acid usually, and they have an anion that's big and complicated usually. We're going to call that IN. So that IN is the anion in the acid that is serving as the acid-base indicator. Now, at a certain pH, due to its own equilibrium, when a pH changes to a certain amount, it's going to change color. For example, here, when the pH is low and there's lots of hydronium, so if we have lots of hydronium, let's say we add lots of acid and we have lots of hydronium, in which direction does this push the equilibrium according to Le Chatelier's principle? Left or right?
Left.
Left, right? So we have more of this, it pushes the equilibrium left. And so we get color A. We're going to get more and more of this and less of this. If we're removing H3O plus, basically by making the solution more basic, that will shift the equilibrium to the right, which results in the other color. And depending on the identity of the indicator, this conversion from color A to color B will happen at a different pH for every indicator, because the color change will happen when the indicator acid gives its H plus to water. So you can see now it's making the indicator anion, its charge is now -1 because it's lost an H plus. When you lose an H plus, you lose the H is gone, and the charge goes down by 1 unit from 0 down to -1. And then the water gained the H plus, so it has 1 more H, and its charge goes up from 0 up to +1. So here's a list of various indicators. You do not have to memorize this list, okay? For your you're not going to need this for your test on Tuesday, but for your test on Tuesday, I'll give you a reference sheet so you don't have to be flipping through the book. For example, with the color wheel and the other things I was going to give you, I'll post that up on Canvas in advance so you can take a look at it. But of course, all our tests from now on are going to be open book, basically open Google, because there's some software called Proctoria they're pushing us to use, but I just feel like having too many tech requirements on you guys is gonna make your life more difficult. I'll have a reference sheet for you. Of course, you can look at anything in the book, but this is a reference on what acid-base indicators, common acid-base indicators are good over what pH range. So let's say you have a reaction where the pH is going to change from a very low pH, like 1, to 3 at a certain point, and you're interested to know when that pH change happens. Well, you should use an acid-base indicator that will change pH, change color around that pH. And so when you're choosing an indicator, you're going to choose an indicator such that the indicator will change color at the same time that the reaction is changing pH, or close to the pH of this particular substance here. And so we can see that we have acid-base indicators that are useful for all kinds of pH ranges. Now, in your general chemistry class, you probably used phenolphthalein as an acid-base indicator for when you were titrating a strong acid with a strong base, and you were adding the strong base. It changes from colorless to pink. The reason why you do this is because the strong acid, strong base titration, as we'll see in chapter 9, you get to the equivalence point when the pH is changing very rapidly from about from around pH 7. And so you will see the color change start to happen just when you pass pH 7, neutral. Whoops. And so phenolphthalein is a great indicator for this strong acid being titrated as a strong base, because when you add enough base to get past neutral pH, it will change to pink. And so these are the reference pH ranges for the color change. And we'll be referring back to, which would be a good indicator to for this particular pH range. And we'll refer back to this diagram. This will also be useful in experiment 8. Experiment 8 will ask you about this, but I also give the pH ranges in the experiment there too. There's a table of them. Okay. So sometimes you won't be given the exact concentration of the hydronium. You'll have to figure it out, whether there's an equilibrium or whether there's not. So for strong acids, there's not going to be any equilibrium, and for strong bases, this is because they 100% dissociate. There is no equilibrium. They just completely separate, or equilibrium is so far towards products that we don't really consider it. So let's think about nitric acid. So let's use your memory banks here. Nitric acid, strong acid or not a strong acid?
Strong.
Strong, right? Remember the strong acids: perchloric acid, sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Those are the 6 strong acids. If it's not one of those, it's weak. So this is going to 100% dissociate. So that's why I have a one-way arrow here. Okay, and when it dissociates, what it's going to do is it's going to give its proton to water. The H plus goes from the nitric acid over here, right? H plus. And so the HNO3 is going to lose an H plus. What will be left of HNO3 is no H, it will be gone. It will be NO3. And is it going to be NO3 with no charge, or is it going to have a charge, the conjugate base?
Can I have a chart?
Charge, -1, right? So we lose an H plus and the charge goes down by 1. So that's what we see right here for the conjugate base of nitric acid. We lost the H plus, so the NO3 is now -1. We lose the H, the charge goes down by 1, from 0 down to -1. Oh, geez. It's going to do this again. Okay. All right. And so this 100% dissociates, and the water picks up the H plus. So now it has not 2 H's, but 3, and the charge goes up from 0 up to +1 because it picked up an H plus. So remember how we were making ice tables and doing our stoichiometry using ice tables? Well, we can still use tables to do our stoichiometry, and we can still do our stoichiometry in molarities. I think most students prefer to do things this way. So if we're doing this, and we'll do more of this in the future, I didn't belabor it on this particular slide, but we can also make what I would call start, change, and end of stoichiometry tables. So for this one, we're starting with 0.025 molar of the nitric acid, and it's 100% dissociating. So that tells us that the change is that when we're done, all of this will be gone until there's none left. Now, water, we don't really care about it. What we care about are the aqueous things. So we're starting with, we're going to say about 0 of hydronium. And this is a little trick we're going to do, because really it's 1 × 10⁻⁷, right? But that is so much smaller than the amount of hydronium we're going to get. We can basically ignore it. And so that's going to be the trick we use for these types of problems. We assume that hydronium is close to 0, and nitrate will have absolutely 0 to start. And so then we'll have plus 0.025 molar for this and plus 0.025, whoops, molar for this. Oh my gosh. And so we'll have 0.025 molar and 0.025 molar. And really, you don't need to do all of this work. You just need to know that this will 100% dissociate. So every time one of these dissociates, it's going to make one hydronium. And that's the hydronium is what we need in order to find the pH. So the way I'm going to represent that is I'm just going to say that since hydronium is a strong acid, it's going to completely dissociate, and its concentration, the concentration of hydronium, will be equal to the initial concentration of the nitric acid. So the hydronium will be equal to the initial concentration of the nitric acid. It will be 0.025. And to get the pH, we take the negative log of that concentration, 0.025. And so we can use our calculator for that. So we have 0.025. We're going to take the log of that, and then we change the sign. And remember sig figs, since this has 2 sig figs, we're going to write this so that it has 2 after the decimal. So we're going to write 1.60, and that will be the pH there. Any questions on how I calculated the pH there? Okay. Now, what if we have a strong base? So the way you recognize strong bases is they are all soluble hydroxides. So our strong bases were going to be group 1 hydroxides. We're talking lithium hydroxide, sodium hydroxide, potassium hydroxide, strong bases. These are strong bases because they produce hydroxide directly in solution. So this is an example of a strong base, sodium hydroxide. And so when we write the equation, we just want to show the production of the hydroxide. So for a strong base, because it's producing hydroxide directly, that is really the only time where we don't include the water in the hydrolysis equation here. The reason is because we would just show water making more hydroxides. So this is just showing the hydroxide directly. So we'll just show that this sodium hydroxide separates into sodium ions and hydroxide ions. Okay. And you may want to put this in your notes. I'm going to type here. Since sodium hydroxide is a strong base, it's a strong base, okay? In case you have forgotten from your previous class, here are the strong bases, okay? And I should insert this permanently into the slides. I think I will. So text box, strong bases, just remember. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, and some of the group 2 hydroxides. This is calcium hydroxide. Also, strontium hydroxide. And barium hydroxide. So those are your 6 strong bases. There are 6 strong acids, 6 strong bases. The other group 1 hydroxides are also strong bases, but we don't encounter them very often. So sodium hydroxide is a strong base we're dealing with here. Okay, and so it's going to completely separate into its sodium ions and its hydroxide ions. And the hydroxide ions are essentially what base is. So we don't need to add water here. It's actually, for strong bases, it's easier to just show the hydroxide being produced directly. So likewise, just like we did for the acid, since we know this will 100% dissociate, the sodium hydroxide is a strong base, so the hydroxide concentration will be the same as the sodium hydroxide. Be careful with these bases that have two hydroxides. If you have calcium hydroxide, it won't just make one hydroxide every time, it will make two. Okay, so that's something to keep in mind. But here, every one sodium hydroxide makes one hydroxide. And so our concentration of hydroxide will be the same as the initial concentration of the sodium hydroxide, 0.025 molar. And so if we want hydronium concentration, though, we want to get the pH right. So when we have hydroxide concentration, that won't get us the pH directly. We need to use Kw. So the hydronium concentration here will be the Kw over hydroxide. And so the hydroxide concentration will be 0.025. So we'll put that in right here. And now we can calculate the hydronium concentration in our calculator. There we go. Calculator. Okay, and so we'll do 1.0 EE, negative 14, divide by 0.025. And we get this. Let's turn it into decimal. It'll be 4 times 10 to the minus 13. Are we going to write it like that? 4 times 10 to the minus 13? How are we really going to write it for the correct sig figs?
4.0.
4.0, 2 sig figs, right? And so that's the way we write it here. 4.0 times 10 to the minus 13 molar. Don't forget the unit. pH doesn't have a unit, but concentrations do. They're molars. Okay. And now if we want the pH, we take the negative log of this. So the pH is going to be the negative log of the hydronium concentration, which we figured out here. So it's a negative log of 4 times 10 to the minus 13 is 12.4. And just, I can show that on the calculator real quick too. So 4.0 EE minus 13, take the log of that and change the sign. So we get we got a 12.39, and we want to round it 2 after the decimal place, so 12.4. And that's how we figure out the concentration for a strong acid or a strong base. Oh, we're past the time. So next time we're going to talk about weak acids and weak bases. What I want to do right now is actually, I'm just going to get you started on the review assignment so that you can do it whenever you want. So I know we're a little over on lecture, but basically what I'm going to do is I'm going to get you started on the assignment so you can start right after if you want or take a break. And then I'm just going to be on and available for you guys to ask questions. So I made a practice exam 2. Let me show that to you guys right now. So if we look down here in exam 2 review, there's a practice exam 2 assignment in Connect. So that's technically what we're doing for lab today. I'm just going to leave the Zoom room open and you guys can feel free to talk to one another, ask questions. I'm also going to start a discussion so you can post in the discussion as well. And so that's the way we'll talk with one another. So we'll add a discussion. It will be exam 2 review discussion. And I'll just save that. And so that's discussion groups are just a place where you can talk to one another. You'll also be able to talk to one another over the mic here as if you're in the same room. I'm just going to leave it open while you're here. I may turn off the screen sometimes, but I'll be here. I'm not going anywhere. So I'm going to put this discussion right there. Okay. And so while you guys are doing this, I'll probably be working on just basically just double checking the problems and stuff. And is a practice exam printable? So there is a printing option. It's not all that convenient though. So the way oops, okay. So here's the assignment, the practice exam itself. It's worth 20 points. You should just be able to go in here and look at the problems one by one, and you can start to complete them. I know for some of you, they load slowly. So as you're working on one, you could start to load the other one. You write it down and start to load the other one. Or print it, although it's kind of cumbersome. Yeah. So you can click the next one. For me, they've been loading really quickly. So I think you should just be able to go through them. Let me know if it's going too slow for you. I can use some of this time to try to copy paste the problem. So what I've done before, it does take me some time. So I really only want to do it if I feel like it's necessary. But what I can do is I can use snip. So I searched on a, what do you call this? On Windows, I search for snipping tool, and then I can snip the problem like that, and I can put it in a Word document. Although I have to do that individually for each problem. So you can see if there's like 40 problems, it does take me a little bit of time, but just let me know, I'm going to be here. But what I think you should do probably is you should work on it in the software, because you're going to be doing it through the software on Tuesday. So part of the experience here is to kind of pretend like you're doing the exam. Now, I'm not going to have 40 questions on the exam. The exam will be a selection of these questions. I'll probably, I'm going to have, I think, 25 questions for the exam, and it'll be worth 80 points altogether. Some of the problems will be worth a little bit more. Like some of these are more like multiple choice questions. They're pretty quick. But if we go down to some of the later ones, they're about like equilibrium and stuff. And so they're a little bit more involved. And so I'm going to put more points on those. This is a Le Chatelier's problem, Le Chatelier's principle. So yeah, some of these involve more, have a little bit more involved calculations. Like this one, what is the equilibrium partial pressure of nitrogen? You've got to solve the ice table and stuff. And so what I'm going to do is I'll be here and available, and you guys can ask me questions when you get stuck. And yeah, and we'll do it that way. And for all the questions that you ask me questions for, I'll be typing them into a Word document. So anything, and I'll just put it in the same place. This will be like, answers to questions during the lab. So the printing function, they're really stingy with the printing. They just let you print like one question at a time. Yeah. I guess what I could do is I could save these as PDF too, each one, and then merge the PDF. That's an option. Yeah. Okay. And then I did want to say before you guys start too, before we kind of go off on our own to do the assignment, I did want to say something about experiment 8. So the experiment 8, the online version, is right here. Experiment 8, actually, I'll just open the document. Now, experiment 8, you probably want to wait till after the test to do it, but I did want to, get you started because you'll be doing the test and then you'll probably do it after at some point. Okay. So here's experiment 8. Experiment 8 involves a number of videos that you watch. So testing for pH. You were going to use a pH meter in here to test for things. So this is just a video showing test. This is a video about how to make the red cabbage juice indicator, which we had available in the lab. You can actually make this at home to test these things if you like. And also this is a video showing about how to use litmus paper. And this is a chart showing a lot of different pH indicators. And for you to choose a pH indicator that would change colors close to the pH of the substance. And so you can fill this in either in Word like this. Oh, the pH is, well, the tap water was, I don't know, 6.8 or something. You can fill it in like that. And then if you do show your calculations, you'll want to show them like I was showing you last time. So you'll insert an equation and so forth. So if we're getting the concentration of hydronium, so let's say I want to put my calculations right after, and I'm doing it in Word. You can either do that or you can just write them on the paper somewhere else. You'll want to insert equation. And so if we were saying, okay, the pH is 6.8, what is the hydronium concentration? Well, actually you could do this without, let's say actually let's say this. Let's say I have the hydronium concentration. It is, so I've figured out the hydronium concentration. It is 2.5 times 10 to the minus 6. And remember, you can use the exponents here when you're writing this. If I want to calculate the hydroxide concentration, I'll probably want to show that in an equation. So the equation is that the hydroxide concentration now I'm going to want a minus in there, so I could choose the hydroxide, and then to put a superscript, I choose up here script and go like that when I'm selecting the OH. Then it will allow me to put a superscript of a negative sign. Then I say equals, and then let's say I want to use a fraction. There's an option up here for fraction. So I make a fraction like that. And this is going to be the K, and then I do a subscript. So script right here, subscript, K, and I want this K in to be the main number, and then so I dragged it over, and then I do subscript like this, W, KW, over the concentration of hydronium, H3O plus. And what I can do is, since I'm putting the subscript next to the H, I choose the H here. I drag my mouse over it, and then I choose subscript. Then I drag my mouse over the 3, and I can drag it into that subscript box like that. And I can do the same with the superscript for the O. I select the O, I choose script, superscript, and then I take the plus and I can drag it into the superscript there. And then I would go on and make another fraction and put in my values. So you can show your work that way if you like, or you can write it in and upload a picture. Again, when you're done, what you're going to do is you'll have your Word document, or you'll have a picture of your Word document. You'll go, let me get into student view. Student view, you'll go to the assignment. You can either get to it in assignments, or you can find it in the modules, experiment 8, and you will submit your assignment, okay? And you'll choose either your Word document or your picture or pictures to upload and submit that lab. So that's how you'll do experiment 8. For next time, in case some of you go and do the practice exam and feel good about it, and I don't happen to talk to you again until the next time, I'm going to meet with you again in the Zoom room here for lecture next time at our normal time, 11 a.m. And then I'm going to show you guys that I'm opening up the actual exam. At that point, you'll have 2 hours to take it. And then you will be free to do the lab as long as you get it done. And so you'll do it for 2 hours. I'll be available on the mic the same way, or on the cam, or on the Zoom rather, the same way I'm going to be for your lab right now. And you can let me know if you run into some type of trouble and I can help you. But you'll have 2 hours to finish it. It will be all multiple choice, just like your practice exam today. And then after that, you can get started on your lab right away or later if you wish. Really, the lab assignments, when you do them is up to you. If you have extra time, you could do it before next week if you really want to. But I'm making it due on April 8th, which is a week from today. So at our Wednesday lab session, you should have it turned in by then. So did anyone want to ask a question about the lab or anything before I let you guys start on the practice exam? The exam will be, when I open it, you'll have 2 hours to finish. So we'll all meet here at 11 so that I know all of you guys are getting ready to do the exam and everything's okay. And then I'll say, all right, I'll show you, I'll say, I'm opening it right now, go. And then you'll have 2 hours to finish. Other questions?
No, I'm good.
Good. Okay, so like I said, I'll probably turn off the video for now, but I'll be here. I'm gonna leave the Zoom room open. So if you have questions, I'll just open the video back. The exam is on Tuesday, yes. So just check the syllabus again, and the exam will be Tuesday, our normal time. I'm trying to make it as much like a classroom exam as possible, but given our technical restraints, the exam is essentially multiple choice now. All multiple choice. I do have one more thing to show you guys. I know a couple people have just started on the chapter 18 assignment. So the chapter 18 assignment, because it had a lot of little questions, its point value was kind of outrageous. So I remade the assignment with a more reasonable point value that's even with all of them. I'm going to show you guys my little calculation for the point value of the assignments, by the way, just so you know. So the assignments, so the way the assignments are going to go, and I'm still building these, you're going to see these pop up into Canvas before our next class, but I've already created all of your assignments for each of the chapters. So the issue with the chapter 18 assignment was that it was like 100-something points and the rest were not close to that. So I brought its point value more in line with the rest. So the chapter 17 had 26 questions worth 52 points, 2 points per question. Chapter 18 has 54 questions. It will be 81 points, 1.5 points per question, and so forth. Also, there are going to be 3 practice exams. The practice exam 4 is essentially, or it's going to be 1 for each practice exam. So that will give you 20 points. And then I'll probably have an extra credit 1. So as you can see here, before the final, I'll have an extra credit 1. So as you can see here, the total for the points is 389 points. However, there are only 300 points allotted for assignments. So if you do all the assignments, you have a potential to gain an extra 89 extra points because the assignments will only be out of 300. So doing all the assignments to completion can get you up to 89 extra credit points. Oh, I said Tuesday? Sorry, no, Monday at normal class time. Sorry about that. No, there's never going to be anything happening that's not at your normal class time. It's always at your normal class time. I'm sorry, I have Monday, Wednesday, and Tuesday, Thursday classes, and yesterday was my Tuesday, Thursday class. So I was in Tuesday mode. Everything is going to go by the schedule on the syllabus. I will say that. Where I misspeak, the syllabus is correct. Okay. And the syllabus says 300 exam points, 300 assignment points, but I have made all of the assignments such that there will be 389 points available. So if you get 300 of the points only, that's the 300 normal points, but there will be also up to 89 extra credit points. Okay. So as long as you're doing all your assignments, your chances of a good grade are very high, but don't cheat, okay? Don't cheat yourself. If you don't understand something, let me know, please. I need to teach you guys, even though we can't be together. And so oh yeah, I read, I got confused too, Tuesday, Monday. Everything's gonna be at normal class time, all right? The final exam will be cumulative, yes. It will be the whole Chem 151. And I will include some questions, about that we had on the review as well, like things about molarity and stuff. So it's going to be our entire class from the beginning to the end. Other questions? The lab final is going to be like the other lab reports that are worth 10 points, except it's going to be worth 20. It's going to be just another lab assignment. So the same way experiment 8 was a lab assignment that you turned in through Canvas, it's going to be a Word document that you can fill out or write on and turn in on Canvas. So the lab exam will be just like lab. All the lab stuff is going to be through Canvas. All the lecture stuff is going to be through Mastering Canvas or through McGraw-Hill Connect. Other questions? Okay, guys, I'm going to end the recording at this point, and I'm going to upload this to YouTube like usual. Again, note it does take a few hours. When it first uploads to YouTube, too, the quality isn't very good, but it re-encodes it into a higher quality as time passes over the next few hours. Okay, so work on that practice exam. Let me know if you get stuck. I'm going to be around, until the end of the lab period, so I can, like I said, I can open a Word document and I'll just type. I'll open, McGraw-Hill Connect in a Word document. It'll look like this. Basically, I'll just pull it up now so that it's there if I need it. I'll have Connect open with the assignment, and I'll have a Word document and a blank Word document, and I'll show you whatever I need to show you. All right, enjoy your practice exam. Try to make sure that you can complete. Now, I'm only going to have 25 questions, but try to make sure that you can complete them in a reasonable time frame. This is kind of like a test run for the exam. So if everything's going slow for you or weird or any type of glitches happen, I'm hoping to resolve them now so you don't have to deal with them when you also have the stress of taking the exam, okay? So that's also the purpose of today's lab period. Okay, and I will see you guys later. Have a great afternoon.
Bye. See you later.
Bye. Say bye, everybody. Everyone can say bye now.
Bye.
Thank you.
Bye.
All right.